Swayam Prabha. Digital India. Educated India.
Write out a mechanism and draw an energy profile for sulfonation of benzene. So the overall reaction of sulfonation of benzene is the conversion of benzene to benzene sulfonic acid. So as shown here, and you need some heat and you would need to add sulfuric acid. So in sulfuric acid, this is a protonated form of sulfuric acid, and just a proton has been moved from here to there. And you can imagine that this oxygen, once it gets protonated, the loss of water can occur, and it produces this SO3 species, which now is well set up to do a reaction with the benzene ring. So once benzene ring, electrophilic aromatic substitution can occur, and this is an equilibrium process, and it can give you this kind of an intermediate, which is a cationic intermediate. And in the next step, there's a loss of H plus that can occur, which is mediated by this hydrogen sulfate ion, which is basically the conjugate base of sulfuric acid. And it's going to give you this benzene sulfonate ion and sulfuric acid. Okay. And now once this is formed, the aromaticity is restored. So we would expect that this process is quite fast. Okay. So one aspect about this reaction that is different from regular electrophilic aromatic substitution is that this reaction requires reasonable amount of heat. And second thing is that it produces an anion, which is benzene sulfonate ion. In order to look at the energy profile, the first step of the reaction is very similar to that of what we would see with an electrophilic aromatic substitution. So you have the benzene ring sort of interacting with the electrophile and producing this delta plus species in the transition state, which then gives you this intermediate that we are very familiar with. The next step is the reaction of the conjugate base here, which is sulfate, to give you so it will be S double bond O minus. So this is the species that is going to be attacking the benzene ring and picking up a proton, giving you the product. One thing to consider here is that given that the first step is a slow step, so the barrier to that first step might be quite high, and also being in equilibrium, the reverse step is also accessible at room temperature, or at the temperature at which we are doing this reaction. So together, the sulfonation of benzene is a reaction that happens which is very similar to any other electrophilic aromatic substitution reaction. Write a reasonable mechanism for the formation of cyclohexyl benzene from the reaction of benzene, cyclohexene and sulfuric acid. Okay, so the question here is that we start with benzene plus cyclohexene and H2SO4. So the question is, what is the product that is formed under these conditions? Okay, so when we have to look at these kinds of reactions, let's just go back to the basics. And what we could expect is that cyclohexene being the more reactive between benzene and cyclohexene is more reactive towards electrophiles. And so we would expect that this picks up a proton from sulfuric acid and it produces a cyclohexyl cation. And now we know from our many examples that we have already looked at, we know that cyclohexyl cation is now going to be a system which can react with benzene, and an electrophilic aromatic substitution can occur, and the product that is going to be formed is cyclohexyl benzene. Okay, when you encounter questions such as these, the right thing to do is to understand the difference in reactivity. So an olefin is more reactive than benzene. For example, we have looked at previously that bromination of olefins is possible, epoxidation of olefins is possible, but benzene itself doesn't react unless you add a Lewis acid, and clearly there is no epoxidation equivalent for benzene under normal conditions. So the reaction shown below gives a single product in 88% yield. The question is, what is the product? Okay, so if I have to understand this reaction, what I need to do is I need to look at the compounds that are reacting. Okay, so here is an acid chloride, and acid chloride, as you know, in the presence of a Lewis acid, can produce the corresponding oxocarbenium ion, and so this is going to be the kind of intermediate that can be produced. And now when I look at 1,3,5-trimethoxybenzene, this, if just by looking at the symmetry of this molecule, all these three positions which are present here, 1, 2 and 3, they are equivalent. So it's almost like a benzene ring in the sense that it's highly symmetric. And so in the presence of aluminum chloride, one of these positions is going to react, and electrophilic aromatic substitution would occur here, and the product that would be formed is the corresponding ketone. So this is the product that you expect from this reaction. What is primary kinetic isotope effect, and how does this help in understanding the electrophilic aromatic substitution reaction mechanism? Okay, so let's now try and understand what a primary kinetic isotope effect is, and using an equation. So the kinetic isotope effect is defined as the rate constant for a reaction that happens with hydrogen, and divided that by the rate constant of the reaction that happens when the hydrogen is replaced by deuterium. Okay, so this is a very powerful technique that can be used to understand reaction mechanisms. So the example that we will take here is the elimination reaction. So as you know, the elimination reaction occurs when you have a bromide, and here the example here that is shown here is the following. So when you have this bromide on the left, what happens is that you expect the elimination to occur. So one of these hydrogens is going to be picked up, and it's going to give you this olefin as the product. Okay, and the base that we use is sodium ethoxide. So what we do is we measure the rate of the reaction and determine the rate constant for this particular reaction. So I can follow the laws of this bromide and the formation of this olefin, and when these are two hydrogens, I can follow the reaction and determine the rate constant. Very similarly, what I do is I replace both these hydrogens by deuterium. Okay, so then what I do is I can then measure the same under similar conditions. I measure the rate of the reaction, and then I determine the rate constant, and the product is as shown here, where the hydrogen is replaced by deuterium. Okay, so now if these two measurements can be done, so OET minus is expected to come attack here and kick out the bromide. Okay, now if these reactions can be monitored, and if the carbon hydrogen bond is involved in the rate determining step. Okay, so if the carbon hydrogen bond, breaking of the carbon hydrogen bond, is involved in the rate determining step, then what we expect is that the hydrogen bearing compound reacts substantially faster than the deuterium bearing compound. Okay, you will probably read about this in one of your later courses, the origin of this effect, but this helps us understand whether the carbon hydrogen bond is involved in the rate determining step. So in this case, we have very good evidence that this hydrogen is involved in the reaction, and therefore we would expect that the carbon hydrogen bond would break faster than the carbon deuterium bond, and because it's involved in the rate determining step, and the kinetic isotope effect for this reaction is about 7. Okay, so therefore from this we can conclude that the carbon hydrogen bond is involved in the rate determining step. Now when we come to electrophilic aromatic substitution, as you know, the mechanism of the reaction, the first step of the reaction is the reaction with the electrophile, and producing this cation, which then subsequently loses a proton to form the product. So in the first step, there is no carbon-hydrogen bond that is being formed or broken, and therefore one cannot expect a primary hydrogen isotope effect. But in the second step, which we have designated as the fast step, there is a carbon-hydrogen bond that is being broken. Now when we do the reaction, we do the experiment where we replace all hydrogens by deuterium and measure the rate of the reaction. What we find is that Kh by Kd equals 1. Okay, so what this tells us is that the breakage of the carbon-hydrogen bond, although it occurs during the reaction, it is not involved in the rate determining step. So because the rate determining step is the loss of aromaticity, which is the first step. So the primary hydrogen isotope effect can be used to understand electrophilic aromatic substitution reaction, because it supports the mechanism that we have proposed, where the rate determining step is the first step. And the primary hydrogen isotope effect being 1 tells us that the carbon-hydrogen bond is not being broken in the rate determining step, but it is being broken after the rate determining step is happening. How many signals would you expect to find in the proton NMR spectrum of each of the following compounds? So there are 4 compounds that are given: 1-bromobutane, 1-butanol, butane, and 1,4-dibromobutane. So from our previous discussions on NMR, we know that protons are equivalent to one another and have the same chemical shift when they are in equivalent environments. So the key word here is the environment. So whatever a particular proton is, the kind of environment that is around it has to be similar. Okay. Usually, in many cases, it's very easy to decide. So for example, if I take the example of benzene, all these hydrogens that are shown here, they have the same chemical shift and they're equivalent because they are in the same equivalent environment. Okay. So methane, for example, is another example where you can clearly say that all of them are equivalent. The last example is tetramethylsilane, which we have seen many times: CH3, 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 and CH3. All the 12 hydrogens are equivalent because they are in exactly the same environment. Okay, but in some cases it may not be as straightforward to understand this, and so what we can do is to mentally replace a proton in a molecule by a test group. Okay, so what I mean by that is that in order to see if 2 hydrogens that you are interested in have the same chemical shift, what we need to do is we need to replace one of them by another atom. Okay, so for example, let's take propane. So propane's structure is shown here, and if I want to understand whether this methyl group and this methyl group are the same, one way to do this is I take this carbon 1 and one of the hydrogens I replace it with chlorine. Okay, so then the resulting molecule that I get is 1-chloropropane. Now I do the same exercise on the other methyl group, which is at carbon 3, where I replace one of the hydrogens by chlorine, and I get exactly the same molecule, which is basically 1-chloropropane. So therefore, if the 2 structures produced by a mental replacement of 2 different hydrogens in a molecule give you the same molecule, then the hydrogens are chemically equivalent. So from this exercise, what we can figure out is that the methyl groups of propane are identical. Okay, so in case of propane, these 6 hydrogens are the same, and therefore this will contribute to one signal, and this this is a CH2 here, and this methylene group would be the second signal, and so therefore the total number of signals that you would see here is 2. Okay, so this is a very, very standard way to identify how many distinct signals are there or are expected in a molecule. So now let's go to the question. The question that we have is 1-bromobutane. So now in this 1-bromobutane, there are 3 methylene groups. So CH2, CH2, and CH2. And then there's one methyl group. Okay. So the methyl group is clearly one signal and there is no sort of dispute about it. Now what we need to understand is whether these two CH2s or these 3 CH2s are similar. Now what I'm going to do is I'm just going to highlight this hydrogen over here, and now if I replace this hydrogen by chlorine, then what I'm going to get is 2 chloro 4 bromo butane. Okay. Now when I replace this hydrogen by a chlorine group, then I get 1 2, or if I have to number it from the other side, then it becomes 1 bromo 2 chloro butane. Okay. So clearly these two are very different compounds. Needless to say, if I replace one of these two hydrogens by a chlorine, I'm going to get an entirely different compound. So therefore, what we can conclude from this discussion is that these 3 CH2s are different. So therefore, you would get 1 plus 3, you will get 4 distinct signals in NMR spectrum. Now 1-butanol is exactly the same until here. You get the same pattern, that is, you're going to get 4 signals as we discussed in 1-bromobutane. The only additional hydrogen here is the OH, and so you would expect 5 distinct signals in 1-butanol. Okay. Now the next compound that we're going to look at is butane. So in the case of butane, what we have is that we have these 2 methyl groups. Let's start with this. Now if I replace this methyl group by a chloro, I get 1 chloro butane, and if I replace this with chloro, then I also get 1 chlorobutane. So therefore these 2 methyl groups are indeed identical. Now coming to the next set of CH2s, if I have to find out whether they're equivalent or not, let me replace one of these hydrogens by a chloro. So then I would get 2 chlorobutane. Now if I do the same thing for this hydrogen, I end up getting 2 chlorobutane. So therefore these two CH2s are also identical. So the number of signals that you would expect to see here is 1 for the methyl and 1 for the methylene. So it will be 2. Now the last question here is 1,4-dibromobutane. So again here there are 4 CH2s, and we essentially need not compare the green CH2s and the blue CH2s, but let's take the 2 terminal CH2s first. So if we replace this hydrogen, one of these hydrogens, by chloro, then you get 1 chloro 1 bromo butane. 1 chloro 1 bromo 4 bromo butane. Similarly, if I replace one of these hydrogens, I get 1 chloro 1 bromo 4 bromo butane. So these two compounds are identical, so therefore the green CH2s are the same. Now if you do a similar exercise with this, you will find that these two CH2s are also identical. So therefore you get 1 plus 1, that's equal to 2 signals. Okay. So now this problem basically shows us that when benzene is reacted with this aliphatic chloride, you end up with a mixture of 2 products. Okay. And so first we will try and tackle why there are 2 products formed, and then we'll try to understand the sort of ratio that is formed and why there's a major product and so on. So as a general rule, so let's say we start with any chloride. So let's say you take RCl plus AlCl3. Okay. So we already discussed this in the class and other things. So you generate basically a carbocation plus AlCl4 minus. Okay. So now when R plus is actually very stable, then it's fine. But if it is not very stable, and if the reaction conditions allow us, then you could actually imagine that there could be a rearrangement of the carbocation, which you have already studied previously. Okay, so let's take this example over here. So let me just number these carbons so that it's easy for us to keep track. So number 1, 2, 3, 4, and 5. Okay, so if we keep the same numbering, 1, 2, 3, 4, and 5. Okay, so here if we keep this as 1, 2, 3, 4, 5. So now that we established this numbering, it becomes quite straightforward for us to address this question. So RCl here is basically 2, 3, 4. So we start with Cl. So 1, 2, 3, 4, and carbon number 5. Okay, so now once you go through the coordination with aluminum chloride and the formation of the carbocation, you would end up with carbocation which is a primary carbocation. Okay, so let's just keep the same numbering: 1, 2, 3, 4, 5. Okay, and we all know that a primary carbocation is fairly unstable and it can rearrange, but nevertheless, if it reacts from this as this carbocation, okay, so then you can imagine that it attacks here, and then it gives you a benzene ring with a positive charge, and there's a hydrogen over here. So then if you just number the carbons, it's 1, 2, 3, 4, and there's actually one more carbon, so we just add this carbon number 5. Okay, so that's carbon number 5 over here, and the rest of the aromatic ring basically remains the same. And then if this gives up a proton, then you'll end up with this product. Okay, now if there was a situation where this carbon number 2 is going to have a hydride, so let me just number it over here. So this carbon number 2 is going to have a hydride as shown here. You could have a hydride migration, okay, and that would give me a more stable secondary carbocation, right? So if I just keep the same numbering, so I am 5, 4, 3, 2, 1. So the positive charge, the hydride has moved from carbon 2 to carbon 1. So that hydride I'm going to draw with the same color, which is here. And there's going to be a positive charge over here. Okay. And now, if this carbocation reacts, then you're going to end up with this product as shown here. Okay. Now, this gives us the framework for explaining the formation of the two products. Okay. But now, how can we account for the compound number 2, I mean the substituted compound on the right being higher in yield? Okay, so what actually happens is that the benzene ring reacts with the primary carbocation, perhaps as soon as it's formed, and some of the carbocation is still available for it to undergo a rearrangement to give you the secondary carbocation. And then the secondary carbocation, being more stable, is going to be, the reaction is going to move towards the right. In this case, the carbocation is going to rearrange and give you a secondary carbocation, and that's going to react and give you the major product. So you can explain both the formation of the product and the ratio using the formation of the carbocation and the stability of the carbocation. Alright, so here the question is, how would you synthesize this compound using the Friedel-Crafts acylation reaction? So because we saw in the previous problem that if you have a Friedel-Crafts alkylation that is going on, then you invariably end up with a mixture of products. So if you attempt a Friedel-Crafts alkylation reaction, then you're going to get a mixture of this compound as well as the rearranged product. So this is going to be a problem, and in fact this might even be the major product. Okay, so in order to avoid this, we want to use a Friedel-Crafts acylation. Now let's look at the steps that are going to be involved. So Friedel-Crafts acylation basically would mean that you break this carbon-carbon bond, and so you have two fragments here. You have the benzene ring, and you would need a carbocation or a oxocarbenium ion such as this. Okay, so this is going to be the most important step. And so if you attack, imagine that there's going to be an attack here, and then this movement of this bond to the C double bond O, then you would end up with product such as this. Okay, so C double bond O, and then you have the ethyl group outside. So this is basically ethyl phenyl ketone, and this can subsequently be reduced. So we'll come to the reduction part. But now the question is, in Friedel-Crafts acylation, you don't see a rearrangement. Now let's look at why, or how do we explain that we don't see any rearrangement. Let's now look at the structure of the acylium cation. So you have a C triple bond O plus, and unlike a carbocation where there's a beta hydride which can move and give you a more stable carbocation when you go from primary to secondary or secondary to tertiary, here the movement of hydride ion can certainly occur, but that will result in a cation that is less stable. Okay, so if we sort of push the arrows, then you end up getting, so if you number this as 1, 2, 3 and 4, then this is 1, 2, 3 and 4, and so your hydrogen ends up here and it's a cation over here. Okay, so if I redraw this, what I get is C double bond O H with a positive charge over here. Okay, so we know that the carbonyl group is an electron withdrawing group, so you can certainly say that this is going to be highly unlikely. Okay, so therefore rearrangement of the acylium cation once it is formed is extremely unlikely, which is why the acylation reaction is more predictable. Okay, now let's go to the next step, which is, it's not difficult for us to now synthesize this molecule, which is this ketone, right? And now from the ketone, we need to get to the final product, which is C, right? We need to get here. So there are two strategies that have been suggested, and the first one is basically the Wolff-Kishner reduction, which is basically a reaction with hydrazine, which is NH2 in the presence of hydroxide ion, usually potassium hydroxide or sodium hydroxide, and then we heat. Okay, so this is the first condition which is used, which is known as Wolff-Kishner reduction. Okay, so this is one way to do it. I would urge all of you to go and look at the mechanism of this reaction. The other way to do it is to use the Clemmensen reduction, which is CLEMMENSEN, Clemmensen reduction, which is basically zinc amalgam in HCl. Okay, so you can use either of these methods, and this is going to give you the product that is desired. Okay, so I want you to go back and revise this concept that you learned previously and look at the mechanism of this Wolff-Kishner reduction. So now let's look at this problem, which is basically the reaction of cyclohexene in the presence of an acid with benzene. Okay, so let's draw out the structures of these two molecules and then reason out what could be the product that is formed. So cyclohexene is basically this, and then reaction with benzene in the presence of H plus. Okay, so benzene is going to be quite stable in the presence of H plus. Cyclohexene, one might imagine that it can actually get protonated. So if it gets protonated, then you end up with a compound such as this, where you have a cyclohexyl carbocation. Okay, and now you can propose that there's an attack by the benzene ring on the carbocation, and you may end up with a compound which is along the lines of this. Okay, so you go through the steps of the Friedel-Crafts alkylation reaction and you end up with this compound. Okay, so the product here is actually interesting because you know that the cyclohexane primarily exists in the chair conformation. So if we were to draw this compound out in the chair conformation, so it would look something like this. Okay, and here you have two choices. That is, the benzene ring could occupy the equatorial position, or you can have the ring flipped isomer, which is here, and here the benzene could occupy the axial position. So just to remind you, this is the equatorial position, and here it is the axial position. Okay, so just for clarity's sake, let me just draw out this hydrogen so that it becomes obvious. Okay, so now the question is, I believe that the stereochemistry is fine, but now the question is, what would be the major product? Okay, so given that there is no other driving factor over here, one would argue that the equatorial substituent, the bulky substituent, which is the phenyl ring, would prefer to occupy the equatorial position, and therefore we would suggest that this compound is the major product.